Over to you, James.
Thank you. So the paper that this is based on is called Private Summation in the Multi-Message Shuffle Model. I'm only going to be talking about the half of that paper that he thought would be of most interest to an MPC audience. I'll start by introducing differential privacy and explaining what the shuffle model is. This is really just to give background for why we're interested in revisiting this paper called Cryptography via Anonymity by Ishai et al. And then I'll explain how we've built on their work, which is really a question of doing secure addition in this anonymity and anonymous channels model. Okay, so firstly, you should recognize this from the previous talk if you were paying attention. Differential privacy, we have some data analysis pipeline, we have a data set which has someone's personal data in it, and we want the output of this analysis pipeline to not leak too much about them. And the way we're going to formalize this is we're going to have another do the same analysis on a different data set, which is the same as the first, except one person's data has been changed. I've been replaced by Elmo here. And we want to ask that an adversary can't really tell between these two situations. And of course, if these two outputs were indistinguishable, then that would mean that nothing about me was being learned. Now, unfortunately, if they're indistinguishable for every pair, then nothing about me is being learned, I'm contributing no information, and then no one's contributing any information, and so we can't learn anything from the output. So that's too much to ask. We can't get utility in that case. So differential privacy instead says that the outputs must satisfy this equation, which basically just says that the probability of the output being in any fixed set can't change too much between these two scenarios, that the likelihood ratio of being in one scenario rather than the other is bounded by e to the epsilon. And you should think of this plus delta on the end as being cryptographically small. Okay, so that's differential privacy in the curator model. Now, there's another model of differential privacy called the local model. And the difference between these two cases is that in the curator model, we were trusting all of the database to some trusted curator who was then going to compute something. And we were merely asking that the output be secure, be private, sorry. In the local model, we instead ask each person to randomize their data locally so that it's already differentially private before they send it into any centralized database. The local model is better because you don't have to trust anyone outside of your own machine to look after your data, but it's also worse because, at least on the question of real valued summation, so this is summing values in the interval 0, 1, with n users, we find that in the local model, it's known that you need to incur error at least square root n, whereas in the curator model, we can get constant error. And the shuffle model has kind of been proposed as something which is intermediate between these two, an attempt to get pretty close to the best of both worlds. And the idea here is that each person randomizes their data and then sends it to a shuffler who will shuffle all the messages together and then send them on to the analyzer. So you do have to trust that a sufficient fraction of the other people, of the other users, will send their data in, and you have to trust that without telling the adversary what they're sending in or how they've randomized it. And you have to trust that they are, you have to trust the shuffler to work. So there's a question, how do we implement this shuffler? This could be with MPC or with trusted hardware or with a mixed net. For the purposes of this talk, we're quite agnostic as to how it's implemented, but there are papers out there discussing, I mean, there's a huge literature on mixed nets, and there are papers discussing how to use trusted hardware to do shuffling in an efficient way. And there are also forthcoming papers discussing how to do it with MPC. So there are ways to implement shuffling. Okay, so then the question is, does this actually give us good accuracy? Do we gain something over the local model by having this shuffling going on? And at last year's TPMPC, I presented a paper in which we showed that we do. In fact, if you're allowed to put one piece of paper into the hat, one message in that's going to be shuffled, then you get error n to the power a sixth is optimal and can be achieved with log n, with a single message of size log n. Chiu et al. Showed that if you have multiple messages. So this is each person is able to write multiple pieces of paper and put all of these pieces of paper into the hat, and then the hat will be shaken and the adversary will look inside. So in particular, the messages from one party won't be linked to each other. Then you can get constant error. However, this requires square root n messages, which is quite a lot of communication. And so this leaves open the question of how much communication do we actually need in order to get this constant error. Also, this Chiratol error, it's order constant, but it's an order of magnitude or two more than that which you can get in the curator model. So there's still improvement to be made on the error there as well. And the way that this protocol is going to work, we're going to, unsurprisingly, it is possible to beat that, and I'm going to show you how to beat it. And it's going to work by first using anonymous channels to do addition. And this allows us to simulate a trusted adder. You know, anonymous channels and shuffling you can think of as the same thing. If you have anonymous channels, well, one way of formalizing that is to say that the messages that are going in are going to be shuffled. And then once we have this trusted adder, we're going to do differential privacy on top of that, show how to use this to get differential privacy with very good accuracy. So let me first do the second of those things, and then I can stop talking about differential privacy for the rest of the talk, and we can just talk about secure addition with anonymous channels. Okay, so our inputs are real numbers. So the first thing we're going to have to do is discretize them. So we're going to round them in a randomized way so that there's no bias in how they're rounded to some precision. And the precision we're going to call P. And then we're going to add some noise to each of the random variables in such a way that when you add them all up, the sum of the noises hides the error. And you might think you want to do something Gaussian-like, maybe a binomial. It actually turns out that you want to use the difference of two negative binomials, because when you add loads of these things together, you get a Laplace distribution. And if you know about differential privacy, you'll recognize the Laplace distribution as being a good distribution to add on top of numbers that have been added up in order to provide differential privacy. And so you won't be surprised that we're getting accuracy very close to the curator model. If you don't need to worry about it. The only point here really is that people are all adding noise, and when they all add together, they get differential privacy. The other point I want to make at this point is that this P, we can choose it to be square root n, and that's precise enough to get us curator model accuracy. So P only needs to be n to the power of half. And then I now want to stop and ask, what have we actually asked of this trusted adder? Is it doing addition in the integers, or in the integers modulo what? And if we have n values, each between 0 and p, then we only need to add values up to pn. Pn plus 1 really, but pn-ish. So that's n to the power 3 over 2. So we need to be able to do addition modulo n to the power 3 over 2 using anonymous channels. Okay, no more differential privacy. I'll move on to how to do addition from shuffling. And the protocol we're going to use isn't new. It appeared in a paper in 2006 by Ishai et al. Called Cryptography from Anonymity. And it goes like this. We have our users, each one has a number. We're going to add these numbers up, modulo 9. They're going to start by additively sharing their values into a bunch of shares, 6 in this case. And then they're going to shove all of those shares into the hat, and it's going to be shaken around, and the adversary is just going to receive effectively the multi-set of additive shares that people put in. And the adversary just then takes all of those shares, adds them together, and gets the answer. Let this protocol is correct, I think, is pretty clear to anyone who understands how additive secret sharing works. So I won't say any more about correctness. The difficult part is proving that this protocol is secure. And in particular, we want to show that if you have two different data sets, X and Y, that add up to the same amount, then the view of the adversary is going to be, or the distribution of the view of the adversary on each of those data sets is the same up to some statistical distance of at most 2 to the minus sigma, where sigma is a security parameter. So this is the kind of guarantee we're providing. And Ishai et al. Were able to do this. They were able to prove that if you take m to be at least this amount here, we had to they didn't do all the constants, they just showed order log n worked. But if you take the constant through, it comes out like this. And it turns out that this is an order log n expression, or sigma plus log n, because q is just n to the 3/2. So log q is log n, or order log n. And if we put these parameters I have in this corner over here in, then we get m equals 89. Okay, so their original proof would have required 89 messages in this situation. But there's something odd about this expression, which is that the number of messages you have to put in is growing with n. If you think about it, when you've got this hat, if you put a certain number of messages, you take your input, you split it into a bunch of shares, you put them all in the hat, and a bunch of other people do, and then you're told that there are going to be more people coming in, and they're all going to put shares in as well. This should make you more secure, not less. And that's not entirely trivial, because in order to have statistical security, we have to protect everyone simultaneously, and there are more people to protect. But you might still intuitively feel like it should, the situation should improve as n grows, not get worse. And indeed, it actually does. This growing with n is an artifact of the proof that Ishai et al. Used. It's not an artifact of their protocol. So there are, sorry. Getting confused about the order of my slides. The point is that here they've shown that if you take m to be order log n, then that works. So we can say if you have order log n messages of size order log n, then you get curator model error. There's something odd about this formula. You shouldn't expect it to grow with n. And indeed it doesn't. So in our work, we showed that this m suffices, which comes out as m equals 14. Meanwhile, in concurrent work, Ghazi et al. Showed that at least if q is prime, then the correct order is this order, which is the same as our order. So they've shown a lower bound, which says that we're both within a constant of the truth. And they also showed an upper bound of that same order. They didn't, however, pull the constants through their proof. We tried to pull the constants through their proof, and were able to come up with solid numbers that worked, but we weren't able to make them very small. And we don't know to what extent that's just because they weren't trying to optimize constants, or to what extent it's a matter of how their proof works, something that's fundamental to their proof. But at any rate, they didn't provide the constants. And if you drag the numbers through here, you get m to be some 3-digit number. So it's worse than the Ishai et al. Result in practice. Okay, and that means that we can get away with big O1 messages. 14 messages would suffice for the situation I just showed you, and give you big O1 error. Right. And this is big O1 of the same order as, it's not just the same order as the curator model, it's within a factor of 2 of the curator model, rather than within a factor of 100 for practical values of epsilon. Okay, so for the rest of the talk, I'm now going to try and explain to you why this protocol is secure, and how we were able to show that it was secure with such a small number of shares. The first step of the proof is going to be to take one share from each of these secret shared values and send it to the adversary. And the purpose of this one share, as far as the proof is concerned, is just to make it so that what remains is doing the protocol with one fewer shares per user, but with an input that is typical. And in fact, the proof goes through even if these 3 values, or these one value from each user that are sent to the adversary, are sent in the clear. The only thing we're going to use them for is making sure that the inputs that we then try to add together using the other shares don't have some special structure that will mess us up. We can assume that they're typical of from the space of n values in ZQ. Okay, so we have typical inputs and at the expense of one share. Now, we want to show that if you have 2 databases that add up to the same amount, here are our 2 databases, that the view of the adversary on one database is almost indistinguishable from the view of the adversary on the other database. is indistinguishable up to statistical security. And the way we're going to do that is to show that if we have one database, then the resulting set of shares that the adversary receives is basically uniformly selected from the possible ordered lists of shares that have the correct sum. So let me first just write down how many there are. There are q to the nm possible lists of shares. One in q of them, i.e. this many, will have the correct sum. And so the probability of being any one of those values should be q to the 1 minus n times m. And what we're actually going to show is that the probability of being any of those one values is less than or equal to q to the 1 minus nm multiplied by 1 plus 2 to the minus sigma. So this is our statistical security guarantee. Okay, and the way we're going to show that is we're going to say if we have two independent runs of the protocol, the view of the adversary in the first one and the view of the adversary in the second one have a probability of being equal that is less than or equal to the probability of them being any one value multiplied by 1 plus 2 to the minus 2 sigma. And this implies that. This is just saying, really, it's because the uniform distribution minimizes your probability of two independent runs ending up on the same value. And so it suffices to prove this upper statement in order to get the lower one. Okay, so we now have two runs of the protocol running on different values. Running with the same inputs, but with different randomness. Okay, so what does this consist of? Well, from each side, we're going to split the numbers into shares, which is what the colored arrows represent. And then both sides are going to be shuffled, and we'll end up with these pairs of black arrows in the middle. And V is going to be equal to V primed if and only if, for every pair of black arrowheads, the number coming from the left is equal to the number coming from the right. Okay, but there's no need to think of two separate permutations here. If you look at the arrow from the middle blue on the left to the lower green on the right, these two arrows meet up here. So we're going to replace them both with just a line that runs from that middle blue to the lower green. And this event is going to be that the value at that middle the value at that middle blue on the left is equal to the value at the lower green on the right. And now comes the bit where I think this is probably the main trick of the proof, really, is that we're going to use the fact that we have these typical inputs. What we've basically said so far is that if we select these inputs, or what we're trying to prove is that if we select these inputs at random and then secret share them and then shuffle them, then we get this nice event happening. But we don't have to think about those random things happening in that order. We could first choose the permutation, i.e. the black lines in the middle, and then choose the shares, and then have the shares determine the things on the outside and ask what's the probability that this event happens. And this probability is not going to change when we consider these things in the opposite order. So let me get rid of those values from the outside and imagine that we've fixed this permutation in the middle. So we're conditioning on this permutation and asking, conditioned on that, what's the probability that we have this event happening? Well, that's the probability that so we're going to consider each black line in turn, starting in the order that they appear on the left-hand side of the picture. And the probability that the first black line has the same value at the left and the right is going to be 1 over q. And we're then going to ask, what's the probability that the next black line has the same value on the left and the right, conditioned on the first value? Conditioned on the first line having the same value at the left and the right. And we'll find that that's also 1 over q. And as we go down all of these arrowheads, each time asking, conditioned on all of the previous ones, matching the corresponding arrow on the other side, what's the probability that this one will also match the corresponding arrow on the other side? And we'll find that as we go down all of them, for this particular permutation that you're currently looking at, the answer will always be 1 over q until you get to the bottom when something different happens, because we're enforcing that the sum of the inputs on the left-hand side is equal to the sum of the inputs on the right. So if all but one of the black lines has a same value at each side, then the final black line must also have the same value at each side. And so as there are n m shares in total, n users, m shares for each, the probability of all of these things happening is 1 over q raised to the power nm minus the 1 from the end, which is q to the 1 minus nm. So the probability of this event happening conditioned on this permutation is exactly q to the 1 minus nm, even without this error on the end. Okay, so I said that that was the case for this permutation. What can go wrong? Well, the thing that can go wrong is that if your permutation doesn't link all the users together, we can try and do the same argument as last time, but we'll find that when we get down to this final blue arrow, because the sum of the green and the blue person must be the same on the left as on the right, once we've seen that all of these first 5 black lines have the same amount on the left as on the right, then this 6th one must as well. And so we don't get a contribution of 1 over q from here. And again, the same as last time, we don't get a contribution of 1 over q from here, from the bottom, from either the bottom blue or the bottom red. And so the final probability is q to the 2 minus nm. But this is the only way it can go wrong. And so in order to understand this error, to bound it as less than 2 to the minus 2 sigma, we need to look at the probability of there being, hang on, let me just say, you can think here of there being a graph where the vertices are the users and the edges are these black lines. So it's going to be a multi-graph with self loops. And this thing that goes wrong, it can go wrong if this graph fails to be connected. So we have some random graph model here, and we want to know whether or not it's connected. And if you're familiar with the connectedness properties of random graphs, then you would probably suspect that the way in which things can go wrong is if there is some isolated vertex, some vertex that is only connected to itself. And indeed, that is by far the most likely thing to go wrong. It's not going to happen that 1,000 of the users over here are all connected to each other and 1,000 of the users over here are all connected to each other, but there are no connections between them. You know, if you have 2,000 users in total, that basically never happens. It's ridiculously unlikely. And so hand waving away the lower order terms, we can just look at the probability of there being isolated vertices and how damaging that is. Okay, so this expression here, the n is the number of users. So this is the number of vertices that could possibly be isolated. The probability of each one being isolated is about 1 over n to the m, which is because they have m shares and each one has a 1 in n chance of connecting to that same user. Again, I'm sweeping lower order terms away. And so this is the n times 1 over n to the m is the probability of this bad thing happening. And when that happens, as you can see on this slide, the probability came out q times bigger than it should be. And so we need this q times that probability to be less than the 2 to the minus 2 sigma that you see at the bottom of this slide. Okay, so that's this expression. The thing on the left needs to be less than or equal to the thing on the right. So if we set them equal and then solve for m, then we get this expression for m. And this tells us how many shares we needed. Remember, there was 1 share at the beginning that we spent in order to get the typical inputs that we needed. And so we need to add that back in, changing this +1 to a +2. And there's also the lower order terms that I waved away. And they can show up again in the form of this constant that is being subtracted from the denominator. So we end up with log in the base 2 of n minus some constant, which is less than 1.5. E is just Euler's number. There's nothing particularly special about this number. This constant can definitely be made smaller than this. But when I was working on that, my co-authors told me that rather than optimizing the constants of lower order terms, I should instead get a life. So this is all you're getting. I hope you understood some of that, and thank you for listening.
Great. There's advice for everyone in the audience. Don't worry about low order terms, get a life. Okay, we have one quick question. Is a question from Antigone. In practice, what do you propose to use to achieve anonymous communications? Is it something like Tor or whatever?
Tor is one possibility, certainly. we have been doing some work on ways of doing this in MPC and of ways of making mixed-net-like ideas be more rigorous and trying to figure out how efficient that is. There are also, I think, a lot of people who are interested in this kind of model from a very practical security viewpoint. I remember giving a talk on this and on this shuffle model, and someone asking, someone from Facebook asking whether it was okay to, or whether this would provide a guarantee if they just collected all the data and then stripped off the metadata and forgot it, would the resulting database then be differentially private? And indeed it would be. So it provides, whilst you have to trust the central authority to strip the metadata off there, it also provides a way of guaranteeing that something is secure there. Obviously for addition, that's not very useful. And I suspect for most of these things, for most of these implementations, it's not going to be the most efficient way of doing addition in that model.
Okay, cool. Right, we'll leave it there. Thank you very much. Another round of applause. And we now pass over to Shai. Shai, can you try and share your window?
Yeah. You cannot start screen share while the other participants.
Oh, you have to, okay. You've got to turn your sharing off, James.
How do I do that? Hang on.
Like that. Perfect.
Okay, cool.
Shai, try yours now. Perfecto.
Right.
Whoa. So we have a huge list of authors, many of which used to work for a bigger company, but they're now working somewhere else. They're working for Algorand. So it's the first time I've ever introduced someone from Algorand. So I'm going to pass it over to Shai, who's sharing the wrong screen. You're sharing your presenter view.
Yeah, I'm not exactly sure how to fix that, but we'll see in a minute.
I think when you do share screen, you can select which window you want to share.
Yeah, but then it switches to the other window. So I need to first start the presentation and then mess with Zoom, which is not clear how to do that.
Maybe put it on presenter mode and then do the Zoom sharing.
Yeah, that's what I'm trying to do. But when it's in presenter mode, then it gives me so much fewer options on the Zoom thing. Oh, I have an idea. Let me try to get rid of the big screen and work only with the little screen, and maybe then it would let me do stuff.
Yay, that works.
Good, thank you.
Right, okay, so over to Shai, and the question is, can a blockchain keep a secret? Shai.
So as Nigel said, this is joint work with Fabrice, Craig, Sergey, Hugo, Chengyu, Tal, and Leo. And the question that we really want to ask, oh, come on, did you hear that? That wasn't planned at all. Turns out that if you don't explicitly clear everything ahead of time, then it shows the... Okay, let's try again. The thing we really care about is, can a blockchain be a trusted third party? And by a blockchain, I mean a public proof of stake blockchain. And by a trusted party, I mean what we always mean in cryptography. This is a party that has clients. The clients give it inputs. They ask it to compute something. Some of these inputs might be secret, but they are, the trusted party would still compute whatever it was asked and give everybody their output and forget about everything else and never reveal anything else about the secret inputs. So this is what we want. And we would like a blockchain to play the role of this trusted party, and can it? And the answer is not really. I mean, blockchains these days are great for things like integrity and immutability properties, but the secrecy story is a lot harder to tell. So in this work, we care about secrecy, and we care about a very basic setting. There is a client of the blockchain, one of these dogs in the previous slides. They have a secret. They want to give it to the blockchain and tell the blockchain what to do with that secret, like reveal it only when the time is right, or more generally, use it only in some prescribed manner that I'm telling you. Here's an example. I publish a puzzle. I give the blockchain the solution to this puzzle, and I tell the blockchain, please reveal the solution if nobody solves the puzzle by next week. So this is a very basic setting, but it can form the basis for many applications. You can do this thing, you can do many other interesting stuff. What we want to achieve, well, there is a security and there is an efficiency consideration. The security is very simple. The secret should remain a secret, that's it. The adversary shouldn't learn what it is, but the blockchain should still be able to recover it when the time is right. Now, this is our solution needs an honest majority, and since we're talking about proof of stake blockchains, then it's an honest majority of the stake. But for this presentation, just imagine honest majority of the participants. Importantly, we considered a mobile adversary. So the adversary can corrupt a minority of the stake this week and a different minority of the stake next week. And even so, we want to make sure that the secret remains a secret. In terms of efficiency, what we're looking for is a scalable solution. And very specifically by scalable, I mean a solution where the communication and the work doesn't increase as time goes by, as the blockchain has more history, or as there are more nodes or more stake. The solution, the complexity of the solution should be some fixed polynomial and a security parameter, and that's it, depending maybe polylogarithmic on everything else. The other efficiency consideration that I call plausible scalability essentially means that we don't want to use obfuscation or things like obfuscation. We want something that can potentially be implemented someday. And in particular, the approach that we use in this work is to rely on proactive secret sharing. So what is a proactive secret sharing? Proactive secret sharing is a long-running system where some secret is shared among a committee. The committee can be everybody, or there can be different committees at different times. But every so often, there is a periodic share refresh protocol where the committee either passes the secret to another committee or just refreshes the secret among itself. And the property is that the secret remains secret as long as each committee separately has honest majority, even if different parties are corrupted at different times. So this is a technique that's been used for 20, 30 years now, and we want to use this type of approach in our solution as well. But there is a problem. In our solution, it's very far from being trivial because I want a solution to be scalable, which means that I can't have everybody participating in the protocol. I need to have a small committee that participates in the protocol so that the solution doesn't get more complex with more people. But if there's only a small committee and if there's a mobile adversary, then, well, the mobile adversary just can corrupt the entire committee, and then it learns the secret and it's all over. So what do we do? This is not the first time that question has been asked, and there is previous work in the setting of a blockchain with committees, but previous work just assume that the committees remain mostly honest. Whereas in our work, we actually design a mechanism to ensure that property. So that's the major difference. And the type of solution that we are using is to keep the committee anonymous. So the adversary cannot target them for corruption. And there's a technique called player replaceability. It's been used in systems like Algorand, where a committee is a one-time thing. If I'm a committee member, all I need to do is send one message, and then I'm off the committee. And once I'm off the committee, I don't have any secrets that I know. So once the adversary know who I am, there is no point in corrupting me anymore because I don't know any more secrets. This is what we want to do. And there's a question of, okay, how do we do that? How do we reshare a secret among committee if we don't know who the committee is? Here are some things that don't work. One way to choose a committee in an anonymous way is for the committee to select itself. So I'm selecting myself to the committee, and the adversary doesn't know that I'm on the committee until I say something via some mechanism called sortition that I'll mention in a slide or two. But this type of thing can't work here. I mean, if I select myself and I don't say anything, how can anybody give me shares of a secret? The previous committee doesn't know who I am. So we don't know how to make that work. Well, maybe in that case, the previous committee can just select the next one. If I'm on the current committee, I'm just going to select my successor in the next committee. Okay, that doesn't work either, because if I'm a bad guy, I will choose a bad guy to the next committee. And if I'm honest, well, then I can choose at random, but still I'm going to hit a bad guy with some probability F. So the committee will have more and more dishonest people as time goes by. And I want to point out that even if I force bad guys to behave honestly by asking them to prove stuff, that doesn't work either, because, okay, so I choose my successor honestly, but I'm a corrupted person, and now I know who my successor is. I can just go ahead and corrupt them after the fact. The adversary is mobile. It can corrupt different people at different times. So that doesn't work either. So what do we do? So the things we observed is that it would really be nice if we can implement the following functionality that I call a target anonymous channel. A target anonymous channel have M visible input ports and M hidden output ports, and some random assignment of the output ports to a subset of the players. So anyone can send a message on the ith input port, and this would be routed to one of the participants, but even the sender doesn't know who the message will arrive to. If we had this type of functionality, then the current committee can just reshare their secret on these M input ports, and these secret will arrive at the next committee. Are just the people that are sitting at the output ports, but nobody knows who they are. I want to point out that this doesn't solve everything. Even if you had that, there's still some work to do, but that's sort of the major problem here. If you could implement that, then other things you can do easier. So how do we do that? We're going to use the three following tools. We're going to use cryptographic sortitions. I mentioned that before. It's based on a verifiable random function, and it's a way for me to select myself to the committee and later on prove to everybody that I was indeed entitled to sit on that committee. So I can toss this coin that with probability P says yes, you're on a committee, and I can prove to everybody that I tossed the coin correctly. So that's one tool. The other things that we need is a PKI and a broadcast channel. And for those, we're just going to use the blockchain. And the third component that we use is an anonymous public key encryption. What that means is a regular public key encryption with semantic security. But in addition, it has this property that if I have two public keys and a ciphertext encrypted under one of them, it's hard to tell whether I encrypted it under the first public key or the second one. So it provides a way for anonymous communication. And with that, I can try to implement some approximation of this target anonymous channels. So I'm going to start with an M members nominating committee that self-selects itself using this sortition mechanism that I said before. So they select themselves, but they don't have any secrets. They don't need to know any secrets. Their job is just to nominate the committee that will know secrets. And then each nominator will choose a nominee among the N parties. And if that nominator is honest, then it will choose the nominee honestly. And if that nominator is dishonest, then it can do whatever it wants. Then what it's going to do is it's going to draw a new pair of public and secret key for some public key encryption scheme. It's going to encrypt the secret key under the long-term public key of the nominee to get some ciphertext. And that encryption is the one where we use the anonymous public key encryption. So the ciphertext doesn't betray the public key or the party that it was encrypted under. And then it's going to broadcast the new ephemeral public key and the ciphertext that encrypts the corresponding secret. What that does is now everybody see this new public key PKI prime and can send messages, can send encrypted messages, broadcast the encrypted messages under this public key. But nobody knows who can see the corresponding messages because the ciphertext encrypting the secret key is anonymous. On the other hand, P sub j, the nominee, can recover the corresponding secret key and then decrypt all these messages. So in a sense, we established an anonymous channel where the target is not known, but everybody can send on that channel. And if the nominator was honest, then the adversary doesn't know who the channel leads to. One important property of this implementation is that we do not ask the nominator to prove anything. So that means that corrupted nominators can, for example, nominate their friends or themselves, or just send publish a completely invalid ciphertext or public keys. And the reason we don't ask them to prove anything, well, the main reason is that proofs just don't work. I already said that before. Even if I force to behave honestly and I'm corrupted, what I can do is behave honestly, figure out who I nominated, and then corrupted that person. So it's not going to help me trying to prove stuff. And also, these proofs are expensive. The statements that I'm going to have to prove are long, in the sense that I'm going to have to prove that there exists some one of these n public keys that's the end, who's the end of that anonymous channel. So this is a statement with long, this is a long statement, so the solution is not scalable. You can still make the proof short, but the work to produce this proof necessarily is long. So let's talk about the resilience of this implementation. The fact that the nominators don't need to prove anything means that the adversary here has a double deeping strategy. The adversary controls some f fraction of the stake or the parties. So because the nominating committee self-selects, it would control roughly an f fraction of the nominators. So corrupted nominators will choose corrupted nominees, but honest nominators, well, they have a probability of a half of choosing a corrupted nominee if they choose at random. So the overall committee will have roughly 2f fraction of corruptions. That means that if we want to ensure honest majority with this implementation of the chosen committee, then we need to assume that the adversary controls strictly less than 1/4 of the stake of the blockchain. So the way the overall solution looks like, we have these nominating committees that select themselves. Each nominating committee then generate these target anonymous channels that lead to the secret sharing committee. And then the previous secret sharing committee will use these target anonymous channels to send their secret forward to the new committee. The resharing by the secret sharing committees require proofs. So if I'm on the secret sharing committee and I send forward some version of my secret, I need to prove that I did it correctly and that the thing that I sent are indeed resharing of my shares. But these proofs are only for short statement with short witnesses. So both the statements and the witnesses are of size that depends only on the size of the committee rather than the entire population. Therefore, this solution is scalable. So the end result is a scalable proactive secret sharing protocol with display replaceability property that I talked about, where as every member talks only once and then it's off the committee. It's secure, assuming that the adversary controls strictly less than 1/4 of the stake, so there's room for improvement here. It can be implemented under all these public key assumptions that we like, except that we actually need to make some conjecture, and I will spend a few slides in a minute talking about that conjecture, about anonymous encryption under selective opening attacks. And there's an open problem here. And that solution can conceivably be made practical. I mean, we didn't implement it. We didn't even try to estimate how complex it would be, but definitely sort of a fixed thing in the security parameter uses only sort of the known techniques of proving stuff about encrypted inputs, and we believe that you can make it practical. So let me switch gears and talk a little bit about the open problem that's the conjecture that we need to make in order to prove security. So our solution broadcasts encryption under anonymous public key encryption, which means that the adversary can see the public keys and can see the ciphertext, and then decides which public keys it wants to corrupt to see the corresponding secret keys. So that brings up the question, so we know that the adversary only corrupts an f fraction of the keys, but can it nonetheless manage to read much more than an f fraction of the encrypted ciphertext? So we have our m ciphertext. They're encrypted under m out of the n public keys. And the mapping of which public keys encrypt what ciphertext is computationally hidden. But does that mean that the adversary cannot corrupt many more of the keys that were actually used for encryption? Right now, I marked these keys in blue. Is the fact that the adversary corrupt only f fraction of the entire population means that it can only corrupt more or less up to f fraction of the blue keys? That's a question. And it's a question about adaptive opening of keys. So an adaptive adversary sees the keys, sees the 5 ciphertext, then decides to open the keys one at a time. I want to see this, the secret key of this public key. Now I get it. Now I want to open the next public key, etc., etc. Another type of adversary that's interesting to talk about is a semi-adaptive. It still sees the keys in the ciphertext, but then makes one-shot decision about which subset of the keys it wants to open, and then gets these secret keys, and there is no more adaptivity after that. If it was secrecy, for the case of secrecy, it's very well known that semantic security does not imply secrecy under selective opening, even if the adversary is semi-adaptive. So we have negative examples of crypto systems that are semantically secure, but nonetheless completely broken under selective opening, even for a semi-adaptive adversary. For anonymity, it turns out that that's not the case. Indeed, we prove a lemma that says that if the public key encryption is anonymous, then a semi-adaptive adversary open at most f fraction of the keys cannot open much more than f fraction of the blue keys, except with negligible probability. So the thing to take home from that is that anonymity behaves very different than secrecy when it comes to selective opening. And we conjecture that the same holds for fully adaptive adversary. We could not prove that. We actually have a reduction that I believe works, but we couldn't figure out how to analyze it. Just a complicated combinatorial game that we couldn't find a handle to analyze. Nonetheless, I believe that that conjecture is true, and this is an interesting thing to try to prove. So with that, I'm way ahead of time, but I'm done with the things that I wanted to say. So let me just state some open problems and future work directions. One of them is to prove the conjecture that I just stated, that anonymous public key encryption is still anonymous even under selective opening attacks. Another direction of future work is to do more with the secret. Don't just keep the secret, actually compute on it. This was our original motivation. We wanted the blockchain to be a trusted third party, which means that it gets many secrets and it computes on them. We actually have some follow-up work that does that. The techniques that we use for sharing the secrets are essentially the same techniques that you can use to compute on it. The difference is not that large. Yet another direction is to improve the resilience of the target anonymous channels. Right now, the implementation that we have, if you want the end result committees to have honest majority, then you need to assume that the adversary control at most a quarter of the stake. And hopefully you can improve it to anything less than a half while keeping the solution scalable. So that's an interesting way to thing to try to do. And the last obvious direction for future work is to try to actually implement this solution. Try to figure out the concrete crypto system that you want to use, the concrete non-interactive zero-knowledge protocols that you want to employ for that purpose, and see if you can get a reasonably practical implementation. And with that, I'm done. Thank you.
Thank you. Okay. Do we have any? Oh, yes. Suddenly, anonymous person. Shouldn't be anonymous. You're not meant to be anonymous. That's what the ICR ones last week. You weren't allowed to be anonymous, so you shouldn't be anonymous. But the anonymous person wants to ask: is the anonymous committee kept secret also after the end of the protocol?
Well, they can't be, right? They have to use the channels to send messages. And once they use the channels to send messages, the adversary learn who they are. If you had anonymous channels from the other direction where you can anonymously post a message, then plausibly you could. Mm-hmm. But that kind of thing, you know, there's no crypto implementation that you can come up with that will give you channels that are anonymous when you post message to. You just have to either you assume that some mechanism like that exists and use Tor or what have you, or you don't. And in our case, we don't assume that.
Does this cause a problem for your application? Because if once you've started using the channel, you know you've revealed yourself, then you can be corrupted, and because you're looking at a proactive model, then you've got a window where the adversary can start hacking people.
Yeah, exactly. Very, very good. So what you do need your PKI implementation to be proactive in the sense that every party broadcasts a new public key once a month or something like that. And you do need to assume that the adversary cannot corrupt people before they broadcast this. And every time that I actually use the protocol, every time that I broadcast a new message in the protocol, I also choose a new long-term key and discard the old one and broadcast the new.
Okay, cool. Right, do we have any other questions? Just let me look on Zoom. No, we don't. Okay, let's thank Shai and everybody else in this session again. Big round of applause. You can all put your virtual clapping by putting your